A voltage regulator is designed to automatically maintain a constant voltage level. A voltage regulator may be a simple feed-forward design or may include negative feedback control loops. It may use an electromechanical mechanism, or electronic components. Depending on the design, it may be used to regulate one or more AC or DC voltages. Electronic voltage regulators are found in devices such as computer power supplies where they stabilize the DC voltages used by the processor and other elements. In automobile alternators and central power station generator plants, voltage regulators control the output to the plant. In an electric power distribution system, voltage regulators may be installed at a substation or along distribution lines so that all customers receive steady voltage independent of how much power is drawn from the line. Measures of regulator quality: the output voltage can only be held roughly constant. The regulation is specified by two measurements. Load regulation is the change in output voltage for a given change in load current. Line regulation or input regulation is the degree to which output voltage changes with input voltage changes, as a ratio of output to input change, or the output voltage change over the entire specified input voltage range. Other important parameters are: temperature coefficient of the output voltage is the change with temperature. Initial accuracy of a voltage regulator reflects the error in output voltage for a fixed regulator without taking into account temperature or aging effects on output accuracy. Dropout voltage is the minimum difference between input voltage and output voltage for which the regulator can still supply the specified current. A low dropout regulator is designed to work well even with an input supply only a volt or so above the output voltage. The input-output differential at which the voltage regulator will no longer maintain regulation is the dropout voltage. Further reduction in input voltage will result in reduced output voltage. This value is dependent on load current and junction temperature. Absolute maximum ratings are defined for regulator components, specifying the continuous and peak output currents that may be used, the maximum input voltage, maximum power dissipation at a given temperature, etc. Output noise and output dynamic impedance may be specified as graphs versus frequency, while output ripple noise may be given as peak-to-peak or RMS voltages, or in terms of their spectra. Quiescent current in a regulator circuit is the current drawn internally, not available to the load, normally measured as the input current while no load is connected. Transient response is the reaction of a regulator when a change of the load current or input voltage occurs. Some regulators will tend to oscillate or have a slow response time which in some cases might lead to undesired results. This value is different from the regulation parameters, as that is the stable situation definition. The transient response shows the behavior of the regulator on a change. This data is usually provided in the technical documentation of a regulator and is also dependent on output capacitance. Mirror image insertion protection means that a regulator is designed for use when a voltage, usually not higher than the maximum input voltage of the regulator, is applied to its output pin while its input terminal is at a low voltage, fault-free or grounded. Some regulators can continuously withstand this situation. Others might only manage it for a limited time such as 60 seconds, as usually specified in the datasheet. This situation can occur when a 3-terminal regulator is incorrectly mounted, for example on a PCB, with the output terminal connected to the unregulated DC input and the input connected to the load. Mirror image insertion protection is also important when a regulator circuit is used in battery charging circuits, when external power fails or is not turned on and the output terminal remains at battery voltage. Electronic voltage regulators. A simple voltage regulator can be made from a resistor in series with a diode. Due to the logarithmic shape of diode VI curves, the voltage across the diode changes only slightly due to changes in current drawn or changes in the input. When precise voltage control and efficiency are not important, this design may work fine. Feedback voltage regulators operate by comparing the actual output voltage to some fixed reference voltage. Any difference is amplified and used to control the regulation element in such a way as to reduce the voltage error. This forms a negative feedback control loop. Increasing the open loop gain tends to increase regulation accuracy but reduce stability. There will also be a trade-off between stability and the speed of the response to changes. If the output voltage is too low, the regulation element is commanded, up to a point, to produce a higher output voltage by dropping less of the input voltage, or to draw input current for longer periods. If the output voltage is too high, the regulation element will normally be commanded to produce a lower voltage. However, many regulators have overcurrent protection, so that they will entirely stop sourcing current if the output current is too high, and some regulators may also shut down if the input voltage is outside a given range. Electromechanical regulators. In electromechanical regulators, voltage regulation is easily accomplished by coiling the sensing wire to make an electromagnet. The magnetic field produced by the current attracts a moving ferrous core held back under spring tension or gravitational pull. As voltage increases, so does the current, strengthening the magnetic field produced by the coil and pulling the core towards the field. The magnet is physically connected to a mechanical power switch, which opens as the magnet moves into the field. As voltage decreases, so does the current, releasing spring tension or the weight of the core and causing it to retract. This closes the switch and allows the power to flow once more. If the mechanical regulator design is sensitive to small voltage fluctuations, the motion of the solenoid core can be used to move a selector switch across a range of resistances or transformer windings to gradually step the output voltage up or down, or to rotate the position of a moving coil AC regulator. Early automobile generators and alternators had a mechanical voltage regulator using 1, 2, or 3 relays and various resistors to stabilize the generator's output at slightly more than 6 or 12 V, independent of the engine's RPM or the varying load on the vehicle's electrical system. Essentially, the relay, employed pulse width modulation to regulate the output of the generator, controlling the field current reaching the generator and in this way controlling the output voltage produced. The regulators used for DC generators also disconnect the generator when it was not producing electricity, thereby preventing the battery from discharging back into the generator and attempting to run it as a motor. The rectifier diodes in an alternator automatically perform this function so that a specific relay is not required. This appreciably simplified the regulator design. More modern designs now use solid-state technology to perform the same function that the relays perform in electromechanical regulators. Electromechanical regulators are used for mains voltage stabilization CAC voltage stabilizers below. Automatic voltage regulator. To control the output of generators, automatic voltage regulators are used. This is an active system. While the basic principle is the same, the system itself is more complex. An automatic voltage regulator consists of several components such as diodes, capacitors, resistors and potentiometers or even microcontrollers, all placed on a circuit board. This is then mounted near the generator and connected with several wires to measure and adjust the generator. How an AVR works: in the first place, the AVR monitors the output voltage and controls the input voltage for the exciter of the generator. By increasing or decreasing the generator control voltage, the output voltage of the generator increases or decreases accordingly. The AVR calculates how much voltage has to be sent to the exciter numerous times a second, therefore stabilizing the output voltage to a predetermined set point. When 2 or more generators are powering the same system, the AVR receives information from more generators to match all output. Coil rotation AC voltage regulator. This is an older type of regulator used in the 1920s that uses the principle of a fixed position field coil and a second field coil that can be rotated on an axis in parallel with the fixed coil, similar to a vario cupola. When the movable coil is positioned perpendicular to the fixed coil, the magnetic forces acting on the movable coil balance each other out and voltage output is unchanged. Rotating the coil in one direction or the other away from the center position will increase or decrease voltage in the secondary movable coil. This type of regulator can be automated via a servo control mechanism to advance the movable coil position in order to provide voltage increase or decrease. A braking mechanism or high-ratio gearing is used to hold the rotating coil in place against the powerful magnetic forces acting on the moving coil. AC voltage stabilizers. Electromechanical regulators called voltage stabilizers or tap changers, have also been used to regulate the voltage on AC power distribution lines. These regulators operate by using a servo mechanism to select the appropriate tap on an auto transformer with multiple taps, or by moving the wiper on a continuously variable auto transformer. If the output voltage is not in the acceptable range, the servo mechanism switches the tap, changing the turns ratio of the transformer, to move the secondary voltage into the acceptable region. The controls provide a dead band wherein the controller will not act, preventing the controller from constantly adjusting the voltage as it varies by an acceptably small amount. Constant voltage transformer. The ferrosonant transformer, ferrosonant regulator or constant voltage transformer is a type of saturating transformer used as a voltage regulator. These transformers use a tank circuit composed of a high-voltage resonant winding and a capacitor to produce a nearly constant average output voltage with a varying input current or varying load. The circuit has a primary on one side of a magnet shunt and the tuned circuit coil and secondary on the other side. The regulation is due to magnetic saturation in the section around the secondary. The ferrosonant approach is attractive due to its lack of active components, relying on the square-loop saturation characteristics of the tank circuit to absorb variations in average input voltage. Saturating transformers provide a simple rugged method to stabilize an AC power supply. Older designs of ferrosonant transformers had an output with high harmonic content, leading to a distorted output waveform. Modern devices are used to construct a perfect sine wave. The ferrosonant action is a flux limiter rather than a voltage regulator, but with a fixed supply frequency it can maintain an almost constant average output voltage even as the input voltage varies widely. The ferrosonant transformers, which are also known as constant voltage transformers or ferros, are also good surge suppressors, as they provide high isolation and inherent short-circuit protection. A ferrosonant transformer can operate with an input voltage range A plus or minus 40% or more of the nominal voltage. Output power factor remains in the range of 0.96 or higher from half to full load. Because it regenerates an output voltage waveform, output distortion, which is typically less than 4%, is independent of any input voltage distortion, including notching. Efficiency at full load is typically in the range of 89% to 93%. However, at low loads, efficiency can drop below 60%. The current limiting capability also becomes a handicap when a CVT is used in an application with moderate to high inrush current like motors, transformers or magnets. In this case, the CVT has to be sized to accommodate the peak current, thus forcing it to run at low loads and poor efficiency. Minimum maintenance is required, as transformers and capacitors can be very reliable. Some units have included redundant capacitors to allow several capacitors to fail between inspections without any noticeable effect on the device's performance. Output voltage varies about 1.2% for every 1% change in supply frequency. For example, a 2 Hz change in generator frequency, which is very large, results in an output voltage change of only 4%, which has little effect for most loads. It accepts 100% single-phase switch mode power supply loading without any requirement for derating, including all neutral components. Input current distortion remains less than 8% THD even when supplying nonlinear loads with more than 100% current THD. Drawbacks of CVTs are their larger size, audible humming sound, and the high heat generation caused by saturation. DC voltage stabilizers. Many simple DC power supplies regulate the voltage using a shunt regulator such as a Zener diode, avalanche breakdown diode, or voltage regulator tube. Each of these devices begins conducting at a specified voltage and will conduct as much current as required to hold its terminal voltage to that specified voltage by diverting excess current from a non-ideal power source to ground, often through a relatively low-value resistor to dissipate the excess energy. The power supply is designed to only supply a maximum amount of current that is within the safe operating capability of the shunt regulating device. If the stabilizer must provide more power, the shunt regulator output is only used to provide the standard voltage reference for the electronic device, known as the voltage stabilizer. The voltage stabilizer is the electronic device, able to deliver much larger currents on demand. Active regulators employ at least one active component such as a transistor or operational amplifier. Shunt regulators are often passive and simple, but always inefficient because they dump the excess current not needed by the load. When more power must be supplied, more sophisticated circuits are used. In general, these active regulators can be divided into several classes: linear series regulators, switching regulators, SCR regulators, linear regulators. Linear regulators are based on devices that operate in their linear region. In the past, one or more vacuum tubes were commonly used as the variable resistance. Modern designs use one or more transistors instead, perhaps within an integrated circuit. Linear designs have the advantage of very clean output with little noise introduced into their DC output, but are most often much less efficient and unable to step up or invert the input voltage like switched supplies. All linear regulators require a higher input than the output. If the input voltage approaches the desired output voltage, the regulator will drop out. The input-to-output voltage differential at which this occurs is known as the regulator's dropout voltage. Entire linear regulators are available as integrated circuits. These chips come in either fixed or adjustable voltage types. Switching regulators. Switching regulators rapidly switch a series device on and off. The duty cycle of the switch sets how much charge is transferred to the load. This is controlled by a similar feedback mechanism as in a linear regulator. Because the series element is either fully conducting, or switched off, it dissipates almost no power. This is what gives the switching design its efficiency. Switching regulators are also able to generate output voltages which are higher than the input, or of opposite polarity, something not possible with a linear design. Like linear regulators, nearly complete switching regulators are also available as integrated circuits. Unlike linear regulators, these usually require one external component, an inductor that acts as the energy storage element. Comparing linear versus switching regulators, the two types of regulators have their different advantages. Linear regulators are best when low output noise is required. Linear regulators are best when a fast response to input and output disturbances is required. At low levels of power, linear regulators are cheaper and occupy less printed circuit board space. Switching regulators are best when power efficiency is critical, except that linear regulators are more efficient in a small number of cases. Switching regulators are required when the only power supply is a DC voltage, and a higher output voltage is required. At high levels of power, switching regulators are cheaper. SCR regulators powered from AC power circuits can use silicon-controlled rectifiers as the series device. Whenever the output voltage is below the desired value, the SCR is triggered, allowing electricity to flow into the load until the AC mains voltage passes through zero. SCR regulators have the advantages of being both very efficient and very simple, but because they cannot terminate an ongoing half-cycle of conduction, they are not capable of very accurate voltage regulation in response to rapidly changing loads. An alternative is the SCR shunt regulator, which uses the regulator output as a trigger. Both series and shunt designs are noisy, but powerful, as the device has a low-on resistance. Combination regulators. Many power supplies use more than one regulating method in series. For example, the output from a switching regulator can be further regulated by a linear regulator. The switching regulator accepts a wide range of input voltages and efficiently generates a voltage slightly above the ultimately desired output. That is followed by a linear regulator that generates exactly the desired voltage and eliminates nearly all the noise generated by the switching regulator. Other designs may use an SCR regulator as the pre-regulator, followed by another type of regulator. An efficient way of creating a variable voltage, accurate output power supply is to combine a multi-tap transformer with an adjustable linear post regulator. Example: linear regulators, transistor regulator. In the simplest case, a common collector transistor is used with the base of the regulating transistor connected directly to the voltage reference. A simple transistor regulator will provide a relatively constant output voltage, out, for changes in the voltage of the power source, Win, and for changes in load, RL, provided that Win exceeds out by a sufficient margin, and that the power handling capacity of the transistor is not exceeded. The output voltage of the stabilizer is equal to the Zener diode voltage less the Bassier-emitter voltage of the transistor, UZ/UBE, where UBE is usually about 0.7 of E for a silicon transistor, depending on the load current. If the output voltage drops for any external reason, such as an increase in the current drawn by the load, the transistor's Bassier-emitter voltage increases, turning the transistor on further and delivering more current to increase the load voltage again. RV provides a bias current for both the Zener diode and the transistor. The current in the diode is minimum when the load current is maximum. The circuit designer must choose a minimum voltage that can be tolerated across RV, bearing in mind that the higher this voltage requirement is, the higher the required input voltage, Win, and hence the lower the efficiency of the regulator. On the other hand, lower values of RV lead to higher power dissipation in the diode and to inferior regulator characteristics. Where Vrmin is the minimum voltage to be maintained across a Vmin is the minimum current to be maintained through the Zener diode. Elmax is the maximum design load current. Phi is the forward current gain of the transistor. I collector/a base, regulator with an operational amplifier. The stability of the output voltage can be significantly increased by using an operational amplifier. In this case, the operational amplifier drives the transistor with more current if the voltage at its inverting input drops below the output of the voltage reference at the non-inverting input. Using the voltage divider allows choice of the arbitrary output voltage between ERS and Win. Commercial use. Voltage regulators or stabilizers are used to compensate for voltage fluctuations in mains power. Large regulators may be permanently installed on distribution lines. Small portable regulators may be plugged in between sensitive equipment and a wall outlet. Automatic voltage regulators are used on generator sets on ships, in emergency power supplies, on oil rigs, etc. to stabilize fluctuations in power demand. For example, when a large machine is turned on, the demand for power is suddenly a lot higher. The voltage regulator compensates for the change in load. Commercial voltage regulators normally operate on a range of voltages, for example 150 a euro 240 a V or 90 a euro 280 a V. Servo stabilizers are also manufactured and used widely in spite of the fact that they are obsolete and use outdated technology. Voltage regulators are used in devices like air conditioners, refrigerators, televisions etc. in order to protect them from fluctuating input voltage. The major problem faced is the use of relays in voltage regulators. Relays create sparks which result in faults in the product. See also: constant current regulator, DC to DC converter, third brush dynamo, voltage regulator module, references. Further reading: Linear and Switching Voltage Regulator Handbook. ON Semiconductor. 118 pages. 2002. HB206/D. Free PDF download.